That's fine. It should be good.
Yeah.
Cool. Alrighty. How are we doing today? Thumbs up, thumbs down, somewhere between. It's a lot of thumbs up. Good to see that. Good to see that. I'm exceptionally tired. Right? I was like super stressed out for 2 days because I had to defend my thesis yesterday. And I defended the thesis. It went great, by the way. Passed it, so I'm like done with that. Thank you. No. Please. Thank you. No. But now that that's out of the way, like all the nerves and the like energy from all that has like faded out, and so I am so tired. Like as soon as I was done, I went home, ate some Subway, slept for 3 hours, then went out for dinner with my advisor, then went to the bar for a little bit, and then went home and slept another couple of hours, and I'm still extremely tired. So that being said, y'all know how I am when I'm tired. I tend to make the little errors in addition. I do that when I'm not tired, but when I'm tired, it happens more. Yes?
Have you decided on the grad school yet?
No, I have not, because I'm still waiting to hear back from half of them. My top 2 choices are North Carolina State if I do mathematics, Penn State if I do physics. So really hoping to hear back from those. Any questions about homework, labs, tests, anything like that? All right. I want to do a review of a problem real quick, and then we're going to start digging into 4.2 and 4.3. So remember when we were talking about a system of equations that has multiple solutions, and I'll use the example that we did. So 1, -1, 0, -0, 1, 2, and 6, and 0, 0, 0, and 0. Right. Remember when a system has multiple possible solutions, like infinite solutions, we just set one of the variables to be a parameter, and then all of the other variables are in terms of that parameter. So I'll let my variables be x, y, and z here. You can do x1, x2, x3 if you wanted. And this is a 0 here, by the way. So since this bottom line, which would tell me typically what the solution of z is in my row echelon form, this bottom line is all zeros, which means I can set z to be whatever. So I'm just going to let z equal t. That's just any real number. And then all of my solutions, my x is going to be in terms of t, my y is going to be in terms of t. So I let z be t, and then my second line tells me that 1y plus 2z equals 6. Right? So y plus 2z is t equals 6, or y equals 6 minus 2t. We're all good with that? All it is I can't tell you what z is. Z could be anything, so all my solutions have to depend on that. If z was a fixed number, all of my solutions would then be a fixed number. So now I have a value of z, and I have a value of y. And I can go to the first equation that tells us that x minus y plus 0z equals -2. And I can use this solution of y to solve for x. So x minus y equals -2. Y is this right here. So x minus this quantity, 6 minus 2t. Remember when you're doing this, when you're subtracting a whole quantity, put it in parentheses, because your negative sign will distribute to your stuff. This is equal to -2. So x minus 6 plus 2t equals -2, or x equals 4 minus 2t. So then I have my solution for x is 4 minus 2t, y equals 6 minus 2t, z equals t, and t is just any real number. So for example, if I let t be 0, then I'd have 4, 6, 0 as a solution to the system of equations. Let me zoom this out. Any questions about this? Because this is about to be used a decent bit in the next couple of problems. All right. So we're in section 4.2 and 4.3 today. So we did 4.2, 4.3a. This was how we're setting up and solving our systems of equations. Here we're going to be applying those systems of equations. Everything that's written on this first page, we did on Monday. Right, so it's just how to set up a system as a augmented matrix, and then use the Gauss-Jordan elimination, where we multiply a row by something, add it to another row, all that sort of stuff. This is what we did on Monday. So this is just listing out again. Specifically, it says for larger matrices, because we were really just dealing with 2x2 matrices. We're just going to do this a couple more times. It's easier to see an example than me tell you what is going on. If you want it written out, it's all written out here. But we'll just go to the example that's on the next page. So we have a system of equations that has 3 variables and 2 equations. One thing that should stick out to you is that if it's not square, I'm going to, if I turn this into a matrix and it's not, a 3x3 matrix unaugmented, then I'm going to either have no solutions or infinitely many solutions. In this case, we're going to have infinitely many solutions. So we'll specifically probably get a line like 0, 0, 0, 0, 0 or something like that. That'll tell us we'll have to have a parameterized solution. So first we want to turn this into our augmented matrix. Remember, that's all the coefficients on this side, a big old line, and then the solutions. So I've got 2x1, 4x2, negative 6x3, and 10. 3x1, 3x2, negative 3x3, and that's 6. One thing that's going to make this a lot easier is I can divide this top line by 2 to get just a 1 here. So 1/2 R1. It's going to be me 1, 4 divided by 2 is 2, negative 6 divided by 2 is negative 3, and 10 divided by 2 is 5. And I can leave the bottom as it is, or I could multiply it by 1/3. Typically, you only multiply one row at a time and then go through, so I'll just multiply that one. So 3, 3, negative 3, and 6. Then in another step, I'll multiply the bottom row by 1/3. So 1/3 R2. So the top row is staying the same, I didn't touch it. 1, 2, negative 3, 5, and 1/3 gives me 1, 1, negative 1, and divide that by 3, I get 2. Anyone with me? Am I terrible at dividing or adding or anything like that? Hopefully not yet. All right. Then, remember, our goal is to get a 1 here and then a 0 here. That's what the row echelon form tells us. So how can I do something here to get this first thing to be a 0? What can I do using this top row? Liam?
Subtract.
Just subtract. Yeah, I'm going to do this bottom row, R2, minus the top row, R1. 1 minus, so I'm going to rewrite the top row because it's just as it is. 1 minus 1 is 0. 1 minus 2 is negative 1. Negative 1 minus negative 3 is negative 1 plus 3, which is 2. And then 2 minus 5 is negative 3. And then I want this to be a positive 1, so I'm just going to multiply this entire bottom row by negative 1. So negative R2. Top row stays the same. 1, 2, negative 3, 5. I get 0. Negative that is 1. Negative 2, and 3. I can't simplify this any further, so I have to set one of my variables equal to a parameter. If I were to write out this bottom equation, and this says x1, x2, x3, but I'm going to just do x, y, z, so I don't have to write subscripts or anything, and it keeps it a little cleaner. So this bottom thing says that y minus 2z equals 3. I can't solve this because I don't know what z or y are, so I'm just going to let z, so I'll say let z equal t. I'm going to let z be my parameter. Almost always when you're doing systems like this, you always just let your last variable be your parameter. So here z is going to be my parameter. So then I rewrite this as y minus 2t equals 3, or y equals 3 plus 2t. So I have my z, I have my y, and then I can plug that in to get x. This equation here tells me that x plus 2y minus 3z equals 5, where y I know is 3 plus 2t, and z is just t. I'll box that in over there so we can recall it. So x plus 2 times this whole quantity of y, 3 plus 2t, minus 3, z is t, equals 5. And then I just solve for x. X plus 6 plus 4t minus 3t equals 5. Move this down a bit. X, I can move everything over, equals, this is a 1t, and this gives me a negative 1. So negative 1 minus t. 5 minus 6 is negative 1. 4 minus 3 is 1. I move it to the other side, I get a negative. So my solution set as a whole is x equals negative 1 minus t, y equals 3 plus 2t, and z equals t, where t is just any real number. Any questions about this one? This again is just what we did at the end of class on Monday when we did this problem right here that I reviewed a second ago. All right. Now we're going to do this in an application. So remember, about a week or so ago, I was telling y'all how to take, a sentence that says, this amount of things and this amount of things is a sum total amount of things, and then they cost this much, like we did with the bushes and trees and the t-shirts and stuff like that. We can do that here with a more complicated system. For example, it says, is that blurry, y'all? It's blurry to me. Turn on the focus on here. That's better, I guess. So it says a company rents trucks. They want to purchase 25 trucks total that have 28,000 cubic feet of storage. There's 3 different types of trucks. So I'm going to let X be number of truck 1, Y is number of truck 2, and Z is number of truck 3. All right. And I want the sum of those to be a total of 25 trucks. Right? It says I want 25 trucks total. So X plus Y plus Z is going to be 25 trucks total. There's also 3 different types of trucks. There's a 10-foot truck, maybe I'll call truck 1 10 feet, that has a capacity of 350 cubic feet. So 350 cubic feet. Truck 2 has a capacity of 700 cubic feet. And truck 3 has a capacity of 1,400 cubic feet. And I want the total amount of cubic feet to be 28,000. So truck 1 has 350 cubic feet. Truck 2, with Y here, has 700 cubic feet. And truck 3 has 1,400 cubic feet. And that should add up to 28,000. All right, so I have a system of equations here that sets up my thing. And I can turn this into a matrix and solve it out. Turning this into an augmented matrix, this top equation just says 1 of x, 1 of y, and 1 of z. That equals 25. This bottom one says 350 of x, 700 of y, 1400 z, and it's 28,000. All right. And that's all we need to do. We can go through and solve out this system. One thing that might be convenient is I might be able to, divide the bottom equation by 10, and that will get rid of just big numbers. I'm going to do 1/10 R2 real quick. 1, 1, 1, 25, 35, 70, 140, 2800. I could simplify that further, but this is all we really need. I'm also running out of space, so I'll use a piece of scratch paper for the rest of this. All right. So I'll write this down first. 1, 1, 1, 25, 35, 70, 140, 2800. I'm wanting to get a 0 here. So I can subtract 35 of this top row. Or, I said I don't need to simplify this out, but I can simplify this out more by seeing what happens if I divide everything in this bottom row by 35. So maybe I'll do 1/35 of R2. The top row is going to stay the same. 35 by 35 is 1. This is 2. This will be 4. And what is 2800 divided by 35? It's 8. All right. Now what can I do to get rid of row 2? Get rid of this using row 1. Someone other than Wyatt. And man, someone other than Wyatt. Someone who hasn't talked yet. Do that.
Subtract R2 from 1.
Yeah, I'm going to subtract. So I'll leave the top one the same. And then 1 minus 1 is 0. 2 minus 1 is 1. 4 minus 1 is 3. And 80 minus 25 is 55, I do believe. All right. I don't have an equation for every variable, so I'm going to have to let one be a parameter. This tells me that x plus 3z equals 55. I'll let z equal t. So x plus 3t equals 55, or x equals 55 minus 3t. That should be y. That should be y, my apologies. Right, because y, z, and then solution. So then this top one says that x plus y plus z equals 25. So x plus, and this is y, 55 minus 3t plus z is t equals 25. So x plus 55 minus 2t equals 25, or x equals negative 30 plus 2t. So my solution options, or my solution possibilities, are x equals negative 30 plus 2t, y equals 55 minus 3t, and z equals t. So there's any number of solutions here, but I want to restrict that because this is an actual application. Does it make sense for any of these to be negative? Why not? You can't have negative trucks. So I want these to be positive. So I want 55 minus 3t. I want that to be greater than or equal to 0. I also want negative 30 plus 2t to be greater than or equal to 0. So one of these is going to give me a larger value for t, and I'll need to use that. Because if I pick the smaller value, it wouldn't satisfy the other equation. This means 55 is greater than or equal to 3t. 55 divided by 3 is 18 and 1/3. So t greater than or equal to 18 and 1/3. This one says 30 is greater than or equal to 2t, so t is greater than or equal to 15. So my solution really should be that t has to be greater than or equal to 18 and 1/3. Does it make sense to have 1/3 of a truck? No, so I need to at least have 19. I need t to at least be 19. All right. So t is 19. T, we'll say, is greater than or equal to 19. And that gives me my restriction. These solutions are good, but t needs to be greater than 19 to satisfy these conditions. Because I can't have negative trucks. I can't have fractions of trucks. I need to have positive whole numbers of trucks. Any questions about that? And again, the lectures are recorded and posted on YouTube if you want to go back and watch over these at any point. So I said t is greater than or equal to 19. Let me write this down on the paper so I don't have to re-reference. X equals negative 30 plus 2t, y equals 55 minus 3t, z equals t. And t greater than or equal to 19. So I can take some possible values of t, maybe 19, 20, 21, and 22, and fill out this chart. So x, number of 10-foot trucks, is negative 30 plus 2t. Negative 30 plus 2 times 19 equals 8. And then y is 55 minus 3 times 19. 55 minus 3 times 19 is a negative 2. Oh, this is not correct. I wrote this incorrectly. Why did I write this incorrectly? I have to flip the sign because I divided by a negative and didn't account for it. So 2t actually has to be less than or equal to 30. So t is in between. T has to be greater than or equal to 15, and t has to be less than or equal to 19. So, 15, 16, 17, 18, specifically 18 and 1/3. So these are allowed values of the truck. My apologies. All right. So t is sandwiched in between these values. So instead of being these values, we actually get 15, 16, 17, and 18. Anyone confused on why I was incorrect to begin with? If you are, please ask so I can clarify. Again, it was because I didn't flip the sign when I divided by a negative in my inequality, so that would give me a lower bound rather than another upper bound. So then plugging 15 into this, I get 30 minus 30, which is 0. 55 minus 3 times 15 is 10. And z is 15. And just to clarify, we really just want to make sure that the number of trucks adds up to 15. 10 plus 15 adds up to 25, so we're good. 10 plus 25. 20 plus 15 is 25. We can do this for 16. What is it? Negative 30 plus 32 is 2. And then 55 minus 3 times 16 is 7. And then 16 here and 2 plus 7 plus 16 is 25. Boy, howdy. Do the same thing with 17. So that's 4 for the first one, and then 55 minus 3 times 17 is 4, and I get 17 here. That does add up to 25. And then this last one, 30 plus 3, so that's 6. 55 minus 3 times 18 is 1, and 18. And that does add up to 25. All right. So these are the possible outcomes such that I don't get negative trucks. So these are the only realistic outcomes in this situation. Then it says that the rental company charges $19.95 per day for 10 foot, $29.95 for the 14 foot, $39.95 for the other one, for the 24 foot. Which of the 4 would produce the largest daily income from rental trucks? So the total cost will just be adding up the cost of each truck. So 15, 16, 17, and 18. Total cost, so 0 times 1995 equals 0. 10 times 29.95 equals 299.5. And 15 times 39.95 is 599.25. And then adding those up, 299.5 plus 599.25 gives me 898.75. And I keep going. 2 times 1995, and I'm not going to equal them out. I'm just going to put all this in my calculator at once. This is 7 times 29.95 and 16 times 39.95. Putting it onto my calculator at once, I'll put it here so y'all can see it. 2 times 19.95 plus 7 times 29.95 plus 16 times 39.95, and that equals 888.75. And then this is 4 times 19.95, 4 times 29.95, and 17 times 39.95. So 4 times, I'm going to combine the next two in one step because they're both multiplied by 4, plus 17 times 39.95 gives me 878.75. By the look of things, the next one's probably going to be 868.95. So 6 times 19.95, 1 times 29.95, 18 times 39.95, and put that in my calculator. 6 times 19.95 plus 29.95 plus 39.95 times 18, and there we go, 868.75. So this one right here, this first option, is the most expensive. All right. So it says, which would produce the largest daily income from truck rentals? This top one. If I tell them to get 10 of the 14 foot and 15 of the 24 foot, that would cost them the most money, so the truck company would be making the most profit. Any questions about this? This, again, is something that we could make Excel do, and this is something that we'll see in the Excel labs. All right. Solving system in Excel. So this, we're just going to set up the problems, and then on Friday we'll go through and solve them in Excel with the lab. So it says a small manufacturing plant makes 3 types of inflatable boats: 1-person, 2-person, and 4-person models. Each boat requires the service of 3 departments as listed below. The cutting, assembling, and packaging departments have a maximum of 38, 330, and 12 lab hours per week, respectively. So then we're set up in this type of system right here. It says how many boats of each type will be produced each week for the plan to operate at full capacity, set up only, and we'll solve it in Excel. All right. So, let's see. What's going on here? So I want to make sure that we don't get mistracked anyway. Each boat requires each of the departments. How many boats of each type? So let the boat types be X, Y, and Z. Right. So the cutting department has a maximum of 380. So sum here is going to be 380. This one's going to be 330, and this one's going to be 120. So the cutting department can spend 0.5 hours on the X boat, 1 hour on the Y boat, and 1.5 hours on the Z boat. So this will be for cutting. This will be for assembling. This will be for packaging. All right. Assembly can spend 0.6 hours on the X boat, 0.9 hours on the Y boat, and 1.2 hours on the Z boat. And lastly, packaging can spend 0.2 hours on the X boat, 0.3 hours on the Y boat, and 0.5 hours on the Z boat. And they'll do this here. It says just to set this up, so we just set this up and we'll do this in Excel. We can also turn this into an augmented matrix, but in Excel, this will be just fine. It says, how is the production schedule in Part A affected if the 4-person boat is no longer produced? So we're going to set this up. So this means that just 0.5x plus 1y equals 380, 0.6x plus 0.9y equals 330, and 0.2x plus 0.3y equals 120. So I just take the Z boat, the 4-person boat, out of the system, and then set up my system of equations again. So here, what does this tell us? It tells us that we have 3 equations just in X and Y. This means that there's no solution. I don't have a solution for these. They're not going to all overlap. So no solution here. Right. The way to think about it is if it's, let me write this down. If it's a rectangle like this, where it's shorter rather than wider, there's infinite solutions. If it's a rectangle like this, where it's taller rather than wider, there's typically no solutions. So I'll say typically. Not always, but for the sake of this class, basically always. So if it's a long, wide rectangle, there's going to be infinite solutions. If it's a narrow rectangle, there's going to be no solutions. The only time that you get exactly one solution is if we have a perfectly square one. And this is just for the coefficient matrix. When we augment it with the solutions, that isn't the same thing. So just talking about coefficient matrix. Coefficient matrix sizes tell us how many solutions we're going to have to our system of equations. We're going to either have 1, infinite, or 0. We don't have multiple, like we won't have like 3 solutions, for instance, at least mathematically. If it's a physical problem like the trucks, then there would only be 4 solutions because I can't have negative trucks. But say in a hypothetical world where there are negative trucks, and there's infinite solutions. Now I've got another example. Suppose the store has 3 size cans nuts. So one is 2 pounds of peanuts, 2 pounds of cashews. I'll call this X. The mammoth size is 1 pound walnuts, 6 pound peanuts, and 2 pounds cashews. So I actually won't call this X. The giant size contains 1 pound walnuts, 4 pounds peanuts, 26 pounds of cashews. Suppose that the store can receive an order for 5 pounds of walnuts, 26 pounds of peanuts, and 12 pounds of cashews how can they fill it with the given size of cans? So the first can contains 2 pounds of peanuts and 2 pounds of cashews. So maybe I'll call, I have peanuts, cashews, walnuts. So maybe I'll let peanuts be maybe X, cashews be Y, walnuts be Z. Yeah, peanuts are X, cashews are Y, and then 1 pound of walnuts is, walnuts I said were Z, peanuts I said were X, and cashews I said were Y. So the large size contains 2X and 2Y and 0Z. And yes, this is the large size. And my solution for X should be that I want walnuts are Z, peanuts are X, and cashews are Y. I want 26 pounds of peanuts. For the next one, for the giant size, for instance, or the mammoth size, so I did the large, now I want mammoth. It has 6 pounds of peanuts, 2 pounds of cashews, and 1 pound of walnuts. And I'm wanting, this is for, this is X, Y is 12 pounds. And then, what is the next thing? I have a giant size, giant. The giant size has, how many pounds of peanuts? 4 pounds of peanuts, 2 pounds of cashews, and 1 pound of walnuts. And my amount of Z is 5 pounds. So this tells me how many the cans added up give me my poundage of nuts. So this solution for X is peanuts. This one is walnuts. And this one is, or this is walnuts, this is cashews. And this is walnuts. So the cans give me the amounts of pounds, and then the solution here would be how many of pounds of peanuts I need, pounds of cashews I need, and pounds of walnuts I need. So we're just setting up the system of equations to be able to solve it out like this. And then again, we will do these in Excel. We'll find the solutions for these. One thing to note is that Excel will give you just one of the possible solutions, so we'll probably need to go through and set some bounds on those solutions when we do them. Like we did for the trucks. There were infinite solutions, but we bounded it to a set of 4 possible solutions. Go ahead and move on to the next section, since we have just a couple of minutes. So reviewing some basics of matrices and how we can act the matrices. Nothing too crazy here, mostly just like adding, subtracting for the first part here. And who all has like done matrix operations, either in high school or anything like that? So a couple of y'all have seen this before. All right. So remember the dimension of the matrix? We count the rows and then the columns. So an m by n matrix, for example, this is 2 by 2. This one is 3 by 2, so I count the number of rows and then the number of columns. Like I go up the left and then the top. The matrix looks like this. I go up here, count that, and then go this way and count it. So this, for example, would be a 4 by 2. 4 by 2 matrix. Remember, we said a row matrix is just a row, right? Just one row of values. Column matrix is just one column of values. It says, what are the dimensions of this row matrix? Well, I go up 1 over 3. So it's a 1 by 3 matrix. Here it says, what's the dimension of this? I go up 4 over 1. Oh, way to remember this is you remember that they're completely unrelated topics, but when you find slope, you do rise over run. You're basically doing the same thing here. You're going up and then over. So count up first and then count over. Just how you count slope. Completely unrelated topics, so don't say that like the matrix is telling me something about the slope of equations. It's just how you count them. It's a way to remember it. A square matrix has equal rows and columns. We call it square because it looks like a square. Two matrices are equal if they have the same dimension and the same entries. So, for example, 1, 1, 2, 3 equals the matrix 1, 1, 2, 3. Very straightforward. If this was a different matrix in any way whatsoever, I wouldn't call them equal. Two matrices can be added if the dimensions are the same. So it doesn't make sense for me to add A, B, C, D plus E, F, for instance. Because like I have this B and D over here, what are they going to do? I can't put them anywhere. So I can only add them if they're of the same dimension. For instance, here, I have two square matrices, and I just add the components individually. So like I add the top left components together, 0.2 and 1.7 is 1.9. Top right, 0.4 and 2.8 is 3.2. Bottom left, 1.8 and or 0.1 and 0.6 is 0.7. And 8 with 4.3 is, what's that, 5.1. So I'm just doing them, this one goes with this one goes with this one goes with that one, and that one goes with that one. Very straightforward. It's just basically combining like terms. It is technically exactly combining like terms, but here we're just combining the same entries of the matrices. This one, can I combine these two matrices? What's the dimension of this first matrix? Up 1 over 3. This one's up 1 over 2. These are not the same thing, so I can't add. Matrices are cool, at least with addition. They obey the same thing that numbers do, right? So if I add A and then B, it's the same thing as I flipped it around and added B and then A. Similarly, if I group them together, if I do A plus B first and then add that to C, it's the same thing as if I did B plus C first and added that to A. So they satisfy commutativity and associativity. One thing that we'll see is that they don't do that when we're multiplying. Multiplying matrices, I can't do this times this is the same as this times this. So that's where matrices start becoming kind of interesting. A zero matrix is just zeros everywhere. So A plus 0 matrix is A. For instance, A, B, C, D plus the 0 matrix is 0, 0, 0, 0 is just A, B, C, D. It's the same thing as numbers. If I add 0 to a number, I get the number back. Subtraction of matrices is the same thing as adding the negative. Note that the subtraction doesn't commute. Subtraction doesn't commute for regular numbers either. What is 4 minus 3, for instance? 1. What's 3 minus 4? Negative 1. So the operation doesn't commute. Specifically, A minus B is the negative of if I were to switch it around. It's negative of B minus A. So I can't just commute the subtraction. That's important there. I have to also have the same dimensions. That makes sense. I can't subtract out spaces that don't exist from a matrix. So if we let A be this matrix, B is this matrix, we could find B minus A, for instance. It helps to write it out explicitly. Negative 1, 0, negative 2, 5, 1, 1. Minus, this is B minus A, 4, 1, 7, 3, 15, 0. This is what? Negative 1 minus 4 is negative 5. 0 minus 1 is negative 1. Negative 2 minus 7 is negative 9. 5 minus 3, or that's 5. 5 minus 3 is 2. 1 minus 15 is negative 14. And 1 minus 0 is 1. So matrix addition and subtraction makes sense. I can also multiply a matrix by a number. All that does is it multiplies everything in the matrix by that number. It's the same thing as when we multiply a row by a number. For instance, if I take half of a row, that's just multiplying that row by a number. And we could think of that row as a row matrix. So for example, if I have A here, 1/3 of A, negative 1/3 of A, and A is 2, 2, 1, negative 4, 0, 5. Note that sometimes I switch between parentheses and brackets. That doesn't change anything. That's just some people write them some way, some people write them the other. I, for some reason, switch between notation very often. This is more natural for me to write because it's just easier to write parentheses, but brackets are just as valid. And I'll multiply by negative 1/3. So that gives me negative 2/3, negative 2/3, negative 1/3. Close it off. Negative and negative is positive, so 4/3, 0, and negative 5/3. Pretty straightforward, and again, all we're doing, we multiply everything in the matrix by that number. Now we can multiply and subtract matrices all together in one equation. For example, 2a minus 3c, I first want to find 2a. That's 2 times 2, 2, 1, negative 4, 0, 5. 2 times 2 is 4, 4, 2, negative 8, 0, and 10. And then 3c is 3 times 1, 0, negative 3, 4, 2, 4. And that's 3, 0, negative 9, 12, 6, 12. Then I want to do 2a minus 3c. This is 2a, 4, 4, 2, negative 8, 0, 10, minus 3c, 3, 0, negative 9, 12, 6, 12. And then what do I get? 4 minus 3 is 1. 4 minus 0 is 4. 2 minus negative 9 is 2 plus 9, so 11. Negative 8 minus 12 is negative 20. 0 minus 6 is negative 6. It's kind of gotten offline because I wrote my 20 a little too big, but that's okay. 10 minus 12 is negative 2. So again, scaling a matrix doesn't change its size, and I can only add or subtract matrices of the same size. And then just this last little example, I'll set it up, and then we'll probably solve it next Wednesday, because remember we have 2 labs in a row. It says Joyce's Jewelry has a kiosk in 2 malls. In May, the location in one mall sold 220 necklaces, 110 bracelets, and 350 earrings. In June, it sold 270 necklaces, 310 bracelets, for 40 earrings. In May, one location sold 130 necklaces, 500 bracelets, for 30 earrings. In June, it sold 470 necklaces, 100 bracelets, 470 earrings. Write a 2x3 matrix that summarizes the sales for each month. So one for May and one for June. So 2 by 3. So our matrix is going to look like this. And maybe this one will be location A, this one will be location B, this will be necklaces, bracelets, and earrings. And then same thing here. So in May, the first location did 260 necklaces, 110 bracelets, 350 earrings. And in May, the second location did 130 necklaces, 500 bracelets, 430 earrings. In June, necklaces, bracelets, earrings, location A, location B. In June, A sold 270, 310, 440. And then the second location is 470, 100, and 470. So again, I can just take a physical problem like this and set it up in matrices like here. And then on next Wednesday, we'll see how we're going to go through and use these matrix operations to get some information on that. Again, if you have questions, text or email me. Those who need to make up the lab, office hours tomorrow morning, text me if you're coming to those, so I need to know how early I get there. Remember, office hours are as early as you need until 12:30.